We've developed a sensor called VECO, which goes inside a driver, and we can detect the coil velocity. And effectively, this is an electrodynamic sensor.
Intuitively, it's very straightforward. So we know the signal that we're applying to the loudspeaker. We know the electromechanical properties of the loudspeaker. So in an ideal world, we should be able to fully predict the velocity of the driver based on that information alone. Of course, in the real world, that is not what happens. Every loudspeaker is subject to some amount of distortion, which will mean that the velocity that the driver is actually exhibiting will be different to what we predict. That's where the VECO sensing coil comes in. It's inside the driver, it's underneath the primary coil, so it's moving as much and as quickly as the primary coil itself. So we have a way of sensing in real time how the driver's velocity is performing.
Now, the real challenge behind this is that a loudspeaker motor is also electrodynamic. So when the loudspeaker is working and you're passing the signal from the amplifier into the voice coil, it's also generating a magnetic field. And in the past, some people have tried to add a secondary voice coil on top of the voice coil that they're driving the speaker with to pick up the velocity. But when you do that, you encounter quite a big problem, which is it starts to act like a transformer. So in addition to a velocity signal on your second coil, you're also seeing some coupling directly from the magnetic field generated by the voice coil to the secondary coil. So what we have is a sensing coil which is printed onto a flexible PCB, and this PCB is wrapped around into a cylinder and replaces the voice coil former.
Now, when you look at the sensing coil itself, so obviously it's wound in a coil, but if you imagine it laid flat, you will see that we have a repeating pattern of winding directions. So we have one that's wound clockwise, then anti-clockwise, then clockwise, then anti-clockwise again.
When these are wrapped around and the voice coil is wound on top of them, they are orthogonal to the voice coil. And what that means is each of those 4 loops is at 90 degrees orientation to the voice coil. And this geometric orientation means that the AC magnetic field generated by the voice coil does not couple to the sensing coil. Now, we need to provide a magnetic field that the sensing coil will couple to so that we can generate EMF in it and detect the velocity. So that means we need to create another magnetic field in addition to the magnetic field that will drive the voice coil. And this field needs to match the orientation of our 4 loops. Now, effectively, when we put these 2 motor systems together, the voice coil and the loudspeaker motor, the sensing coil and the sensing motor, these 2 motor systems are uncoupled. They cannot see each other and they can coexist independently. We can drive current into the voice coil and create force to push the diaphragm, and we can independently pick up the velocity on the sensing coil. When the loudspeakers are operating, the voice coil is fed with an electrical current which represents your music signal, and the loudspeaker motor creates a force which pushes the diaphragm. When the voice coil moves, the former goes with it and the printed PCB goes with it. And on the secondary coil, we get a change in flux due to the secondary motor system that generates an EMF. And that EMF is proportional to the velocity of the cone. And we can take that velocity and feed it back in a negative feedback loop, which means any error that appears on that velocity we can correct for in the loudspeaker electronics. And this means we can get much better control over the loudspeaker cone motion. We can effectively have a damping factor which is below 0, much more control that you can get with a normal voltage amplifier. The overall result is better controlled bass and lower distortion bass. And if we run that without the sensor attached, the cone motion is completely out of control. It's way too much. And one of the beauties is that we can control that by closing the feedback loop, and we can precisely define exactly how much we want to feedback and how much we want to control the motion. And that gives us the ability to regain really good tight bass, really good clean control of the low frequencies of the loudspeaker. Adding a sensor to our active systems has been on our radar for a long time, but actually developing the sensor has been a huge undertaking. Now we have it, we're starting to explore the possibilities of how we can use that signal and how we can best improve the performance of our products. Even on the first attempt, we're getting some really great results, and it'll be exciting to see how far we can take this in future.